And so today, this talk is I will review our work done in the around past 10 years on the lens and the accommodative system. And this is also because 10 years ago, that's when I started my PhD. So it's exactly 10 years. And also today, my PhD student has also come, and she has continued on the same topic. And she will give a detailed introduction about our most recent work. So the eye lens, we know similar like the cornea is a major refractive component of the eye. The lens contributes to about 1/3 of the eye's total optical power. And on top of this function, it can change its shape to bring the focus at different distances. And this is because the lens has elasticity. And we know that with age, that around 50 to 68 years old, people can no longer focus on near objects. And that's the condition of presbyopia. And it's mainly because there's a loss of the lens elasticity. And also on the other hand, we know that the aging of the optics can lead to the other disease, cataract. So when we look at the lens function, we really need to focus on both its physical properties, both the biomechanics and the optics. So the visual accommodation, we all know it's the process of the eye to change focus. But the exact mechanism of how this process happens is actually still undetermined. There are several theories existed in currently that describe such process. But unfortunately, these theories, more or less, they have contradicting descriptions to each other. So for instance, the most well-known theory by Helmholtz, he says that the three zonules, all the zonules, they behave the same in changing the lens shape. They are all taut in seeing far, and they are all relaxed when the eye is seeing near. And also there's this Shaker series, which he says that only the equatorial zonule is the truly active component in changing the lens shape. The anterior and the posterior zonules only serves as a supplement to maintain the lens in a stable position. And also there's this Coleman theory who additionally introduced the contributions from the anterior membrane of the vitreous. So we can see that the whole process of accommodation is actually an interplay between force and deformation. And that's why it is important to look at the visual system from biomechanical aspects. So today my talk will be divided into two parts. The first part about the mechanics of the lens itself, and the second part is about how the lens interacts with the surrounding structures. To begin with, because I can see from the agenda there are only two sessions on biomechanics, so I think although some of you already have the background in biomechanics, it would be still good for me to give some introduction about the fundamental concepts needed in this field. So let's consider a cuboid, which has a cross-sectional area of A and a length of L. And if we apply the two forces in opposite directions, but in the same axis to this cuboid, it will elongate. And this kind of load is called loading in normal directions. And if the two opposite forces are only parallel to each other, but not in the same axis, that will cause some kind of shear deformation. And this is called shear loading. And if we want to describe a material's behavior independent of its shape, we need to involve the concept of stress and strain. So stress is the force applied to the unit area, and strain is a unitless concept describing deformation. And there are two sets of equations for the normal and shear loading conditions because the directions for some terminologies are different in these two conditions. And we can see from the animations on the right side, the lens, when during accommodation, it actually deforms by a number of different zonules in different directions. So actually inside the lens, there are stresses. It's a mixture of both shear and the normal stresses. And then the next concept is about elasticity and viscoelasticity. So elasticity describes such a material property when it is applied with a load and then the load is removed. Its stress-strain curve in the two directions follow exactly the same path. And it if the path is linear, it is called linear elastic. But if it's not linear, it's non-linear elastic materials. And when the loading and unloading curve do not follow the same path, and that's viscoelasticity, and that's when time plays a role in dominating the material's behavior. And for viscoelastic property materials, there are two very common phenomena called creep and relaxation. How to understand these two phenomena? We can imagine there's a soft tissue, and if we apply the soft tissue with a constant load, it will continuously deform. And on the contrary, if we apply the tissue with a constant deformation, a constant strain, its internal stress will gradually be released. And that's creep and relaxation separately. And we also have a mathematical and physical models to describe the elasticity and viscosity behavior. For elasticity, we normally use a spring. That is, the force is linearly related to displacement. And however, for viscosity, the force is actually related to the rate of the displacement. And if we connect the spring and dashpot in parallel or in series, we can actually describe different types of the viscoelastic behavior. And the complete description of the whole accommodative system using the spring dashpot was actually described about 30 years ago. And in this model, the lens was represented using a void model. That's a dashboard and a spring in parallel. And the other structures, such as the zonules and the coil, they were treated as of elastic behavior and were modeled using the springs only. So in this model, the far to near accommodation and near to far accommodation were considered separately. Because according to, in those times when the Helmholtz theory was most widely accepted, according to his theory, when the lens is seen near, it becomes a more convex shape with its surrounding zonules relaxed. And that's why the far to near accommodation is only dominated by the viscoelastic properties of the lens itself. However, on the other side, when for the near to far accommodation, the properties of the zonules and other structures are also involved. So they derive two time constants to describe the two opposite processes. And in engineering world, we have the saying that structures determine the property. So to understand the lens biomechanics, we need to look at its structure. The lens, we know, is a laminar structure which contains the long, thin fiber cells compact tactily within the lens capsule, layer by layer. And inside the cell, the cytosolic protein concentration actually varies spatially. They are the highest in the center, but it gradually decreases to the periphery. And this spatial inhomogeneity actually contributes to, it is the basis for the optics and mechanics spatially varying property. And also because there are protein concentrate solutions inside the lens, it has some kind of viscosity. So in summary, the lens property is actually viscoelastic, inhomogeneous, and as a biological tissue, it keeps changing with age. So it is in a dynamic state. Now we can go through some classical methods and how these methods have been applied to the human lens in assessing the mechanical properties. So the seminal work was the spinning lens test developed by Fisher. And he used a rotator to hold the lens and spin the lens at different speeds. So in this method, the lens can deform to a flattened shape, which was thought to mimic the deformation during accommodation. And we can see the picture's comparison for a young lens with a lower speed of spin, about 1,600 rounds per minute, and in comparison to an old lens which was spin at an even faster speed. The young lens deforms much more than the older lens, suggesting there's a properties difference. And Fisher, especially, he calculates the modulus using mathematical models by dividing the lens to different layers. And this is actually, I think, the early concepts of finite element analysis. That's the theoretical calculation. And then later on in 2011, the spinning lens test was repeated by an Oxford group. And especially they have used this computational simulation method to replicate the experimental process. And they use an inverse finite element method to deduce the lens material properties. And that is to let the simulation search over a range of different properties and find the one that can best fit to the geometry change captured by the camera. So the benefits of using finite element analysis is that you can assume the distribution of the materials. For instance, this group, they have considered three different grade distributions. The first one, by assuming the lens is the elastic modulus is constant. And secondly, by treating the nucleus and the cortex separately. And the third one models spatially varying in modulus from the center to the periphery in an exponential form. But it's a pity that in their test, they have removed the capsule from the lens. Therefore, during the spin, the waters may dry out by the centrifugal force, and therefore the influence to the results cannot be estimated. And there are other non-invasive measuring methods that can keep the lens intact. And here shows the apparatus developed by Glasser and Campbell. So they have used a plunger to compress the lens. It moves up and down. And then at the bottom of the lens, there's a pressure transducer that can monitor the relative resistance. And by applying like a similar amount of compression to lens samples of different ages, their relative stiffness can be compared. So they found that the lens stiffness actually increases continually with age. But they didn't calculate the exact modulus because at that time, maybe factoring out the contributions of the shape is not that easy. And then another method, the bubble acoustic radiation, which applies use ultra-fast laser to create microbubbles inside the lens tissue at different locations. And then a transducer was used to apply acoustic radiation to the bubbles and track the resultant displacement of this bubble. And it is thought that the displacement pattern here will contain the information of the material's local compliance, which is the reciprocal of the Young's modulus. And using this method, they can measure a range of different locations inside the lens. And apart from that, there are also invasive measuring methods that require cutting the lens into halves or getting thin slices from the lens for conducting the measurements. But these we know that because the lens has this highly arranged fiber cells, and by cutting will actually disturb the fiber alignment. And in their methods, they have used a cylindrical probe to indent the lens tissue at different locations in the equatorial lens. And by tracking the indenting force and the indenting depth, they can calculate the modulus of elasticity. And then another study, they have also employed the method of finite element analysis for the calculation. And they found that the distribution of the elastic modulus across the lens, it changes with age. So in the center, it is more pliable in young age, but it is more stiffer in old age. And now we can make a summary of all those results reported by these different studies. We first look at the studies that report nucleus and cortex separately. And it's clear the general trend, the increasing trend were similar. Both the nucleus and the cortex, they continuously increase with age, but different speeds of increase were reported. For instance, Fisher says that across the lifetime, the nucleus is always more pliable than the cortex. But the work by the Oxford group and also by Hayes using the indentation method, they say that there's a crossover between the nucleus and cortex modulus around 30 or 45 years old. And then by converting, because some reported shear modulus and others report Young's, and this can be related by treating the Poisson's ratio as an 0.5 to calculate, and then we make a comparison of these values directly on the graph here. And also, there are other the indentation method that measures the spatially varying properties across the equatorial plane. We see that in young age, the center, it has a lower modulus than the periphery, but the center keeps increasing and increasing. So in middle and older ages, they are much higher than the periphery, and that's the general trend. And for detailed and a summary of the methods or the results, you can refer to the review by Barbara and me we published several years ago. So now it's time to review some of our own work on the lens mechanical measurements. And we first started with the parallel plate compression measures using a commercial instrument. So this instrument can give us the values of the force and displacement curves. And we can fit this curve using some mathematical equations. And we started the fitting using the contact mechanics by Herzen. So there is a classical Herzen model describing contacts between plate and spheroid. And then we try to validate our calculation using finite element analysis. We found inconsistent results. And then searching through the textbook, we found it is because the Herzen model only applies to the situation when the deformation is very small. And so we have adopted this cracking coefficient alpha to account for this discrepancy. And using the simulated results by finite element analysis and then compare with the experimental data, we can actually conclude alpha value of 1.5, which applies to the situation for measuring the lens. And so this actually gives an idea of how experimental measurements, the mathematical model, and computational simulations can be combined all together for evaluating the mechanical property. And however, we know that the compression actually cannot deform the lens in a manner that's exactly the same to accommodation. Because you can imagine the fiber cells near the lens pool, they were actually being squeezed rather than stretched. So we have further developed an automatically controlled stretching system by ourselves, and that has 8 loading units. So the basic design concept of this stretcher is the adoption of arching median curve. You can see here. And the nature of this curve is that imagine there is a point moving along the curve. The movement in the radial direction and the movement in the tangential direction along the curve, they can both be kept at a constant speed at the same time. And so this feature allows us to use an electric motor driver to control the rotational movement easily, because this can guarantee the distal movement of the 8 loading units can also be moved in our self-defined speed. So we then we produced the stretchers using some the 3D printing method in combination with some standard sliding units. And our model were then experimentally validated using Poisson eye samples. And here you can see the graduated rotation of this stretcher and also the distal movement of the 8 loading units. You can see that the lens being stretched and into a larger shape. And also, we know in recent years there are new technologies which can measure the mechanical properties of the lens in vivo. And as a representative, the brilliant light scattering has been successfully applied to a human lens over a wide age range. Although says mechanical measuring methods, the basic principle of this technique is actually still based on optics. So the general idea is that when the light ray passes through the sample, it will encounter an upshift and a downshift of its frequency, which is called the Stokes and anti-Stokes scattering. And this frequency shift will contain the information of the mechanical properties and can be used to calculate the longitudinal or bulk modulus. It should be noted that these types of modulus are different from the Scher or Young's we introduced in previous slides. because bulk or longitudinal modulus it actually describe volumetric material behavior. But Young's and shear modulus, they are directionally based. So these two types of modulus can only be converted to each other under the condition when the Poisson's ratio is not close to the critic value of 0.5, but which is actually the case for most biological tissues. So for lens, it is actually hard to compare these two types of measurements directly. And then when we're looking at the data reported by the gradient light scattering analysis, we found a very interesting phenomenon. That the distribution of this longitudinal modulus in the lens is very similar to the refractive index profile. And these profiles were measured by Bauer using the synchrotron facility in Japan. So this suggests that there may be some link, the potential link or relationships between these two physical parameters. So with this question, we have conducted a series of modeling work. So our first idea was to create a lens model with zones that represents the zones of this continuity when you can will from optical measuring method. So we constructed the geometry we take the geometry of the lens from optical images reconstructed using the green data, and then rotate the geometry by 90 degrees without the solid model in SolidWorks. And then the solid model was further imported into an ANSYS mechanical APL software that's for finite element analysis and also for discretization. And on the right side, that we assign firstly we assign a step. We also call it gradient distribution of the modulus in the cortex to different layers. And we considered a different number of layers in the cortex. So then we made a comparison among models at 3 different ages, including the 16, 35, and 48 years old. And we also compared 2 sets of material properties, either reported by Fisher or by the Oxford group. And it is interesting, we found that when the cortical modulus is lower than the nuclear modulus, the highest stresses, that's the last column here, the highest stress is concentrated to the requitor equatorial region of the nucleus. But when it is opposite, there is a clear stress boundary between the nucleus and the cortex. And we also found that the stress becomes more evenly distributed as the number of cortical layers increases. And then in a follow-up study, we would like to further investigate whether the material or geometric change can play a major influence to the accommodative decline. So to do this, we have adopted 2 approaches. The first one is to restore the 2 older lenses with material properties of the younger one. And the second approach is to reshape the 2 older lenses with the shape of the younger one and compute their resultant central optic power. And we found that both approaches can restore the accommodation to some extent, but reshaping the lens gives a more restoration. And then we moved a step forward to model the linear changing elastic modulus in the lens cortex. And that's, as we said before, the lens actually, when we investigate it is the optical properties, the mechanical properties, and the protein concentration is actually the link between the 3 fundamental properties. And the link between the protein and the refractive index has already been found and been settled. It is only how mechanics is related to the other 2 is uncertain. And then we look at the data the Bauer actually measured in Japan. We found for refractive index data, the magnitude actually do not change very much with age. It's actually the width of the central plateau region and also the stiffness of the periphery that keeps change, and which is also the case for the gradient light scattering analysis. So we have created a series of lens models using the ratio between the plateau region to the whole lens. And then we have write a code in ANSYS by ourselves to assign material properties to different nodes using a linear interpolation method. And that is, the nuclear has a constant Young's modulus, which decreases gradually towards the surface. And this approach can be applied also because we have a structural match. So the nodes are distributed in a structured way. And in total, we consider 3 different types of the model settings and 8 different ages and 2 zonal configurations. And perspective, you can see high stresses or stress or sharp change of the stress is normally what we expect from soft tissue or from any structures. And also, the radial model produces a lower amount of deformation compared to the uniform model, but they produce similar amount of optical power change. So that means the linear changing, radial changing modulus is really a smart strategy for accommodation. So now we can move to the next section about how the lens interact with the surrounding structure, and more specifically with the zonules. The name zonule was actually given by an anatomist in 18th century, who is called Johann Lin. So the Lin's name, so it's also called the Lin's zonule. And zonule is derived from Latin word zona. Zona means belt or girdle, so zonule means little belt. And the zonule, you can imagine it has a very clear engineering purpose. The first one is to keep the lens in the center, lens centration, and the second one is to mediate accommodation. So now there are, from anatomical studies, we know it's difficult to build the zonules in vivo, so all these informations were actually from anatomical structures. And then we actually, from the literature, we found actually 5 groups of zonules can be identified nowadays. This includes the anterior, equatorial, and posterior zonules that connects to the lens equator to the ciliary process. And also another one, the fourth one, pars plana zonule, that connects to the ciliary process to the posterior end of the ciliary body. And we also have this vitreous zonule, which was found in recent years, that connects the ciliary process to different locations of the anterior hyaloid membrane. So actually, there are 5 sites that has direct or indirect relation with the lens shape change. So let's quickly go through how the different groups of zonules were thought to play a role in the existing accommodative series. We know that harmful series is very common to all, that when the ciliary muscle contracts, the zonules all relax and the lens returns to a more spherical shape. And this series actually has the one that has been supported by many in vivo experimental methods. So they found that with increasing accommodative stimuli, the anterior and the posterior radius curvature, they decrease, and the thickness increase. So however, the harmful theory was opposed by some researchers because from a logical way of thinking, a relaxed muscle cannot hold a zonule with tension, and that's what physiologically think. So Scherning, a later scientist, he proposed that the contraction of ciliary muscle actually increased the zonular tensions, and that caused the lens to bulge forward. And he attributes this forward bulging to the different material properties between the nucleus and the cortex. But this idea has not been supported by many researchers at that time. And also there's this Coleman theory. He especially considers the zonules, the anterior membrane of the vitreous, and also the lens capsule as a complete diaphragm. And so when the ciliary muscle contracts, that will cause a pressure difference between the anterior side and the posterior side. And that will push the lens to the forward direction. And so there will be a steeper curvature in the lens center and a flattened curvature in the lens periphery. And then in recent years, there's this Shaker theory, as introduced before. He divides the functional zonules into 3 sets, and it's actually the equatorial zonule that stretches the lens during accommodation. And that will stretch the lens into this like spindle shape. And the anterior and posterior zonules, they remain taut all the time, but they only serve to remain the lens in position, but not involved in accommodation. So to understand the zonular functions, we started to model the zonular angles. And we first considered 3 different zonular apparatus. The first one is the one has adopted in most studies to combine the 3 zonules to a single stretching point and stretch the zonule along the horizontal direction. And in model B, we have then altered these models to different angles, either anteriorly or posteriorly. And for model C, we have provided the 3 zonules with ability to move into different directions independently. And then we have applied the stretching loads at 6 different levels and calculated their optical power using this sequence formula. And then the resultant changes in the curvature as a function of the accommodative amplitude was plotted, and it's very clear it's a linear relationship. And this linear relationship can be compared with some previously in vivo measured data. And we found that for model A, it can only provide a good fit for the anterior surface. And for model B, by changing the angle, a good fit for the posterior surface can be found. And only for model C, when all the 3 angles were altered, a balanced fit can be determined. And that's why we have continued to develop an exhaustive search approach by combining ANSYS and MATLAB. So it is an automatically generated simulations algorithm. So we can simulate about 1,800 combinations of angles for each lens model. And we found that for some particular lens geometry and under certain zonular angle combinations, both the anterior and posterior fits can be found. That's when the warmer the color means the better is fits, and when the warmer color overlaps with each other, that's the best fit of the zonular angle. And then we further expanded our model to whole eye model to include more structures. And this is our whole eye model that contains the 5 sets of zonules we introduced before. And especially, we have developed a pre-stress modeling approach. So we can actually model the far to near accommodation, which is thought the positive process of accommodation, which is different from the majority of the models in the literature, because they only apply stretching to the lens. That is actually when the eye changes from near to far. So with this pre-stress approach, we then further considers the independent role of different zonules by a number of different comparison models by cutting 1 zonule in each model. And then we can compare their resultant central optical powers to see the contribution. And this work was published last year. And then we continue to explore the zonular functions and also the material properties using geometries from 2 age cohorts. That's either in the age of 40s or in the age of 60s. And my PhD student will give a detailed introduction about this work in the coming session. And then finally, its acknowledgement, I would like to thank Barbara for all this year's support, and also thanks to my students for their hard work on this topic. Thank you.
Mina, thank you so much for a brilliant presentation. I think we'll take questions at the end, yeah? Everybody, or how do you want to do it? Okay, no questions. Any questions? Thinking about them. Yeah? You've been spared the questions, Kehao. Thank you very much.
Thank you.
Again.